Hi everyone. Thanks for signing up for today's live broadcast on spectroscopic ellipsometry for organic electronics applications. I'm Joanne Lowy, Marketing Manager at HORIBA Scientific and moderator for today's event. For more than 20 years, HORIBA Scientific has provided a wide range of spectroscopic ellipsometers with a wavelength range from VUV to NIR and the capability to perform ex situ, in situ, inline, and large area measurements. HORIBA Scientific's spectroscopic ellipsometers use of stationary phase modulation technology provides the most sensitive ellipsometric measurements. Applications benefiting from this technique include characterization of semiconductors, flat panel displays, optical coatings, biotech and surface chemistry, and photovoltaics. This webinar will focus on applications of spectroscopic ellipsometry applied to the emerging field of organic electronics, which allows for low-cost, flexible, and lighter electronic devices for applications such as smart windows and electronic paper. We'll also show that thickness and optical constant determination and control is critical for optimum device performance, and why spectroscopic ellipsometry provides needed information without damaging the samples being measured. Before we begin, there are a few important announcements. First, the slides will advance automatically. Next, feel free to ask questions during the webinar. You can submit questions by typing them in the Q&A box on the bottom of the presentation window. If you have any technical questions viewing or hearing this presentation, please click on the question mark Help widget in the dock at the bottom of your window. Now I'm going to introduce today's speaker. We're pleased to be joined today by Dr. Michelle Sestak, Application Scientist at HORIBA Scientific. Dr. Sestak earned her PhD in physics from the University of Toledo, where she applied the technique of spectroscopic ellipsometry to study thin-film cadmium telluride solar cell materials and devices. She graduated in June of 2012, and shortly after she joined HORIBA Scientific as an application scientist in Thin Films Division. Through her role of supporting customers at HORIBA Scientific, Michelle has gained extensive knowledge on applying spectroscopic ellipsometry to many different materials in many various application fields. Now I'm going to turn the presentation over to Michelle.
Okay, thank you, Joanne, and thank you everyone for joining us today. As Joanne mentioned, I'm going to be discussing spectroscopic ellipsometry for organic electronics applications. As a brief outline, we'll go through a short introduction to spectroscopic ellipsometry. This is more or less a basic overview for people who are not familiar with the technique, and this is going to give some idea as to what ellipsometry is and what you can use it for. After that, we'll give a short introduction to organic electronics, basically, again, what they are and how they're used in several different kinds of devices. And then we'll look at some spectroscopic ellipsometry examples on 3 different types of organic devices. So the first will be organic light-emitting diodes, organic solar cells for the second, and light-emitting electrochemical cells for the third. Finally, we'll follow up with some conclusions. So the first question to answer is, what is ellipsometry? So ellipsometry is a powerful, non-contact and non-destructive optical technique for thin film applications. It's based on a polarization change after oblique reflection off of a sample. So if you take a look at the picture on the right, we send in light of known polarization state, typically linearly polarized light, obliquely reflect off of a sample, and then at the end we end up with elliptically polarized light. And this ellipse is where ellipsometry gets its name from. So this ellipse holds information about the sample itself, and we'll see what kind of information we can get by analyzing the ellipse that comes after reflection off the sample. Ellipsometry has 2 parameters, psi and delta, and these describe that output ellipse, and they're related to the electric field and the polarization state of the light. Ellipsometry is an indirect model-based approach. So since it's model-based, you need to have some prior information about your sample so that you have good starting values for your models. Ellipsometry can be spectroscopic or single wavelength, and in this presentation we'll focus on spectroscopic ellipsometry. And it can be used to measure thin film thickness, optical constants, and a lot more, as we'll see. So what are the advantages and of course the disadvantages of spectroscopic ellipsometry? The advantages are that it's non-destructive, non-invasive, and non-contact. There's really no sample preparation necessary. Has a quick measurement time. It's a very sensitive technique for measuring ultra-thin films. And we have the capability to measure both single and multi-layer stacks. Of course, the disadvantages are that it is model-based, so you have to have an optical model, which again, you need to know some prior information about your sample before building the model. And in some cases, you end up with very complicated data analysis. Ellipsometry measurements should also be confirmed with other techniques, such as glow discharge, SEM, TEM, etc. So what information can we get from spectroscopic ellipsometry? The two most common things are film thickness and optical properties. But once you have the optical properties and you have the model, you can obtain surface roughness, interfacial mixing, composition, crystallinity, anisotropy, depolarization, optical bandgap, alloy composition, and uniformity by both depth and area. So that would mean grading of index through the film, as well as mapping the sample to see changes in thickness and index. So what types of thin films can be used for spectroscopic ellipsometry? I'm going to say that most of what I say here is dependent on the system that you have. So it can really vary from system to system. But in general, you want specularly reflecting samples where the roughness is much less than the wavelength of the light. You have a thickness limit that ellipsometry can determine, and that, again, depends on the instrument choice and the type of the sample that you're working with. So transparent materials, I'll say around 60 microns is the cap for thickness determination. May be able to go a little bit higher, again, based on the instrument that you have. Whereas for metals, we say around 60 nanometers is the thickness cap, because metals are highly absorbing. These can be graded, anisotropic, depolarizing samples. And we can do ellipsometry measurements on curved surfaces, patterned surfaces, contaminated samples, as long as the features are large enough, such that the beam of light is over the entire feature. And this can be on flexible or rigid substrates, such as silicon, glass, plastic, etc. And on substrates no larger than about 50 millimeters thick. So again, this depends on the Z height capability of the stage that you're using in your ellipsometer. So the general quick overview of SE data analysis. How does this flow work? First, we take a measurement. We end up with some raw data. We build a model. And again, we give the model some starting parameters, something that we know about our sample. So a starting thickness or starting optical constants. We know, say, which layer is which, and we know what the substrate is, everything that we know about the sample. And then we do a fit and check how well that model fits to the data. We use a regression analysis, make some changes to the model, and keep doing the fit until we get a good fit. And then you end up with the results. So your thickness, optical constants, roughness. So a lot of times we get the question, how do I know if I have a good model? So as far as assessing the results, you can check chi-squared, which is the goodness of fit parameter. That'll tell you how close your model matches your data. You can check the correlation matrix, which will tell you if any of your fit parameters are correlated to each other. So typically thickness and index can be correlated. So if there's a way that you can decorrelate certain parameters, you should certainly do that. And then we check the overall thickness and index values. So we ask, are the results physical, and do the results make sense? Just a quick note in this slide, I have two of the graphs in photon energy and one of the graphs in wavelength. So I just want to bring up real fast the conversion between energy and wavelength. So wavelength is equal to 1240 divided by the energy in electron volts. And similarly, the energy in electron volts is equal to 1240 divided by wavelength in nanometers. So we'll switch back and forth in this presentation, but they're just a 1/over relationship. So when I say, are the results physical? Well, there's certain optical constants that you would expect for certain types of materials. So you want to make sure that your optical constants are behaving as they should. And when I say, do the results make sense? We're checking the error bars on the numbers. We're checking the numbers themselves just to make sure that they're in the range that we expected. And we're checking, again, the overall results to see, is this what we would expect for our sample? Another main question is, what about spectral range for spectroscopic ellipsometry measurements? So of course we have the visible range, and then we have an extension to IR and extension to UV as well. So where do these come in handy? As far as the IR, this is to obtain thicknesses of materials absorbing in the visible. It's also for ultra-thick samples. So in the IR, you'll see many more interference fringes, and you'll have good resolution for the interference fringes. It's good for IR active materials and free carrier absorption, so you can obtain carrier concentration, carrier mobility, and conductivity. On the other end of the spectrum in the UV, this is useful to have for bandgap determination, crystallinity, and composition determination. It's for absorption of dielectrics and semiconductors, ultra-thin films, low index contrast film stacks, alloy composition, and you can ultimately determine grain size as well. So I wanted to give two quick examples on how we use the UV to determine crystallinity. So this is an example of three different curves. The red is crystalline silicon. The green is a 50-50 mix of amorphous silicon and crystalline silicon. And the blue is amorphous silicon. So if you look at the red curve for crystalline silicon, you end up seeing that the peaks are typically very sharp. And then as the material becomes amorphous, you start to see a broadening of the peaks. And if you look at the green curve, it's sort of somewhere in between the crystalline and the amorphous, which it is. It's a 50-50 mix. So features in the UV are helpful to determine crystallinity of your samples. Another use of the UV is for bandgap. And NAR as well. The aluminum gallium arsenide optical bandgap varies with varying aluminum concentrations. So as I increase the percentage of aluminum, my bandgap increases, shifting the absorption edge to shorter wavelengths. So I can see from different compositions how the optical constants can vary. So what exactly are optical constants? We'll focus on using the terms index of refraction, or little n, which is the ratio of the velocity of light in vacuum to its velocity in the medium. So n is simply c over v. Nk, which is the extinction coefficient. And k is the amount of absorption loss when light propagates through the material. I also want to talk about dispersion because it's important for spectroscopic ellipsometry. So dispersion is a variation of optical constants as a function of wavelength. So typically when you look up a value for refractive index, you see one number, and that value is typically given at 632.8 nanometers. But in reality, refractive index actually varies for different wavelengths. So it has what we call dispersion. There are two main types of dispersions. First is a normal dispersion. Normal dispersion is where n decreases with increasing lambda. K is equal to 0. And transparent materials are where we see normal dispersion, so dielectrics and insulators. The other type would be anomalous dispersion. For anomalous dispersion, n increases with increasing lambda where an absorption peak occurs. And K is, of course, not equal to 0. And this is dispersion that is used for absorbing materials, such as semiconductors, many of the organic materials we'll talk about today, and transparent conducting oxides, etc. So I want to go into dispersion functions. So dispersion itself can be mathematically modeled by using dispersion functions. And basically, they're equations that describe the dispersion. And we're going to talk about 4 examples in this presentation as they apply to organic materials. And I'm not going to get into these too deep because they're quite complex, and this would be a whole webinar in itself. So just a quick overview. A Lorentz oscillator is used for transparent or weakly absorbing samples. A Drude oscillator is used for metals, and you can typically use a combination of Drude plus a Lorentz for transparent conducting materials. A new amorphous oscillator is for semiconductors and organic materials, like we'll see here today, and a tau Lorentz is the same thing, semiconductors and organic materials. Of course, there are many other dispersion functions, probably around 30, to describe different types of materials, and sometimes you do need to use multiple dispersions for some of the samples that you're working with. So I'm going to switch over now to organic materials. What are organic materials? Basically, materials composed of carbon. And there are 2 types that are used in organic electronics. The first is small molecule, and these are things like pentacene, AlQ3, and PCBM. And the second is polymers. And in this case, we're going to see in one of the examples a polymer called super yellow and the polymer P3HT as well. So as far as characteristics of organic materials, the advantages are that eventually they will be inexpensive. They have the ability to be inexpensive. They can go through easy processing at very low temperatures. These are inexhaustible materials. They're very colorful and they have a strong interaction with light. They have mechanical flexibility and high thermal stability. So again, you have low temperature processing with mechanical flexibility. This is very good for flexible substrates and flexible devices. You can vary the optical and the electrical properties via doping. So we'll take a look at an example of where doping comes into play. And organic materials, as I kind of said already, they're ideal for large area, flexible, and roll-to-roll applications. Of course, they also have their disadvantages. And one of the main ones is that they have sensitivity to oxygen, light, and water vapor. So they degrade very quickly. Of course, you can encapsulate them to make the device last a little bit longer. And of course, the cost. So the cost is currently high just due to the immaturity of the technology. So we would hope as these are developed more that the price would come down. So as far as the potential for organic electronics, right now we do see organic electronics in everyday life. We see them in smartphones, televisions, computers, in the displays, digital cameras, and virtual reality headsets. But the future applications can be endless. So I've listed just a few here. We're talking about flexible smartphones, flexible televisions, flexible computer screens. And this is where displays can be printed onto foil using organic inks. And once printed, they can be rolled up. So you can have a rollable newspaper or a rollable computer, something that's very easy to transport. Another application here is transparent solar cells on Windows, phones, and laptops. So you can always have solar cells also for clothes as well, to be charging your devices and things like that throughout the day. Have another one, electronic skin that mimics human skin, and biosensors, and also illuminated wallpaper for room lighting. So the organic electronic devices that we're going to look at in a little bit more detail today are organic light emitting diodes. And of course, there are many different materials that an organic light emitting diode can consist of. So we're just going to go through one example. This might not be the same materials that you're currently working with or plan to work with, but these techniques that we'll see here can be applied to other materials as well. So the important information from spectroscopic ellipsometry for these OLEDs is thickness and optical constants, and the materials we'll be looking at are ALQ3, NPB, and copper thiocyanine. Second device will be organic solar cells. The important information from spectroscopic ellipsometry here will be thickness, optical constants, composition, index grading, and band gap. And we're going to look at a specific example again of P3HT and PCBM. And the last one will be light emitting electrochemical cells. So the important information here, thickness and optical constants of a complete encapsulated device. So I'll give you some tips on how to measure and analyze an encapsulated device. The materials involved here are that super yellow polymer, which we'll get into just a little bit more, KTF, and PEO. So for the first example, the organic light emitting diode, it's basically a device which consists of an organic layer or a series of layers, and it emits light when electric current is applied. So it's a pretty basic device. It's used again to create digital displays in televisions, smartphones, and monitors. It can consist of two different types of materials, like we saw previously, small molecule organic materials, which is where the focus is for this presentation, and polymer organic materials as well. And there's no backlight needed, so these devices can be lighter, thinner, and more flexible than a liquid crystal display. They have an excellent contrast in low light, and they also have very low power consumption, which is very important. On the right, you'll see an example of an organic light emitting diode. Again, this is just one example. There's many structures that you can have, many different materials that you can have. The materials that we're looking at here include ALQ3, which is a tri-8-hydroxyquinoline aluminum, or an aluminum salt, and this acts as the electron transport layer. Then there's a doped ALQ3 layer, which acts as the emissive layer, and you can change the color of the organic light emitting diode based on the dopant, the doping level, and the structure of the ALQ. So we'll see the optical property difference between ALQ3 and doped ALQ3. NPB is a naphthol-phenyl biphenyl, and this acts as a whole transport layer. And a CuPC is a copper thiocyanine, and this acts as the whole injection layer. So overall, the thickness and the optical properties of all of the layers in this device are critical for best device performance, or what we're really looking for is maximum recombination. So what we're going to go through here is how to actually characterize this full device, and we're going to do it step by step. So for SE analysis of multi-layered structures, it's helpful to have each component of the device as a single layer, preferably a bulk layer, to first obtain the optical properties for each material. And this at least gives you a starting point for each material so that your correlations in the end are reduced when you're trying to fit 5 or 6 layers. So what we're looking at here is, of course, the structure of ALQ3. And this can be a very basic sample of ALQ3 or doped ALQ3 just on glass, so a very basic one-layer sample. And you can see the difference in the optical constants for the actual ALQ3, it's the dots, and the doped ALQ3 in the line. So you can see as we dope ALQ3, we change the optical properties of the actual ALQ3 itself. So it's important to know these optical properties and what's actually happening with the ALQ3. For those of you who do know ellipsometry, I just want to point out some different kinds of oscillators that are used for these materials. So at the bottom of the screen, you'll see how these are actually modeled. So the ALQ3 and the doped ALQ3 are modeled based off of a multiple new amorphous dispersion. So the second step here would be to characterize the single layer NPB to determine its optical constants. Again, this is a single layer of NPB on glass, and you can see the resulting optical constants for NPB. And NPB is modeled, again, off of a multiple new amorphous dispersion function. The third step here is to characterize the single layer of copper thiocyanine to determine the optical constants again. So here's the CuPC molecule. This is CuPC on glass, and you have the optical constants of that material. And just like the others, and this is typically, you'll see a trend here, we can also model this with a multiple new amorphous dispersion function. What's also important for the organic light emitting diode is the ITO layer, mainly because it's inhomogeneous in depth, so we call it graded. It has an index difference from the bottom of the layer to the top of the layer. So what you'll see here is basically you have the graded ITO layer on top of glass and the resulting optical constants. So the dots are at the top of the sample, the line is at the bottom of the sample. So we have some index change, a linear index change, as a function of where we are in the ITO layer. This ITO is also modeled based off of a multiple new amorphous dispersion, but now we've included a Drude dispersion as well for the metallic character, the conducting character. And also this can be modeled also by a combination of Lorentz or tau Lorentz oscillators plus a Drude oscillator. So there are different ways you can model these samples. Finally, you have the whole stack. So this is the SE measurement and analysis of the entire OLED stack. The optical constants are all fixed to those that were already determined, and we're basically fitting for the thickness values of the layers in the stack. So you'll see on the right some raw ellipsometry data and the fit results, and on the left you'll see the thicknesses for each layer in the sample. I'll move on to organic solar cells. And these are devices which consist of a series of organic layers. And they're designed to provide light absorption and charge transport to produce electricity from the sun. These consist of organic electron donor and acceptor materials rather than semiconductor PN junctions, as in traditional inorganic solar cells. Again, they can consist of two types of materials: small molecule organic materials, such as PCBM, or polymer organic materials, such as P3HT. These are thinner, lighter, and flexible when compared to traditional inorganic solar cells. But currently, cell efficiency is lower than for inorganic solar cells. Cost is also potentially higher at this point, but again, the materials are fairly new and not as much research has been performed on them. So as time goes on, we expect the price to come down. So the same thing here, you have the structure for the organic solar cell. This is a P3HT PCBM solar cell. P3HT is a conducting polymer, and it's considered the electron donor material. And PCBM is a fullerene derivative, which is considered the electron acceptor material. So we end up with an active layer in the solar cell, which is a mixture of P3HT and PCBM. Here we want to put a focus on the blend layer, the P3HT PCBM layer, because device performance is strongly related to that layer. So we're interested in the blend composition and morphology, the crystallinity, the phase separation, and the layer thickness as well. Just as we did in the last example, we'll break this down step by step, single layer samples. So first you have to characterize a single layer of pure PCBM on silicon. So you see here, we ended up with a thickness of 506 angstroms of pure PCBM on silicon. And over on the right, these are the optical constants for that PCBM. And you see what we call the fingerprints of the PCBM, which are basically the peaks in the extinction coefficient. So just zoomed in a little bit there. PCBM, just like all the other materials that we discussed, is also modeled based off of a multiple new amorphous dispersion function. The second step here is to characterize a single layer of pure P3HT on silicon. So this is 935 angstroms of pure P3HT on silicon. And over here on the right are the optical constants of the P3HT. And just like we did for the PCBM, we look at the fingerprints of the P3HT. So the peaks, the absorption peaks, and what wavelengths they're at. P3HT, just like PCBM, is modeled based off of the multiple new amorphous dispersion function. Putting it all together, we want to characterize the blend layer of P3HT and PCBM. So we can take two different modeling approaches here. The first is using an effective medium theory, and we basically have some blend on top of silicon, and this effective medium theory ends up giving information about the morphology, so the grading and the phase separation of these blend layers. So effective medium theory takes percentage of one material and adds it to percentage of another material to give an effective optical constant set for that layer. The other way that we can characterize this is as a single homogeneous layer. And this can provide insights into blend film composition and crystallinity. And again, we're looking at those fingerprints for P3HT and PCBM. So we're interested potentially in the peak amplitude, the broadening, and some other things there. So you see, for the effective medium approximation, or the effective medium theory, we end up with some percentages of P3HT and PCBM. This is a graded layer. The P3HT is, there's more of it at the top of the layer and less as you go down. So there's some gradient there. And in the single layer, you just assume there's no gradient, that it's just a mixture. So I want to do a quick comparison of extinction coefficients for pure PCBM, pure P3HT, and a P3HT PCBM blend. So we saw these already. This is the optical constants for pure PCBM, along with the fingerprints, and the optical constants for pure P3HT, also showing some of the fingerprints. The blend material contains the fingerprints of both the PCBM and the P3HT. The last example we'll go through is for light-emitting electrochemical cells. These are devices that are based on electroluminescence, and basically that's emission of light in response to an electric current. They're similar in structure, applications, and benefits as OLEDs, but there's also additional benefits. And the benefits include that you can use materials such as graphene or a blend of carbon nanotubes and polymers as the electrode, and you can thus eliminate the use of the indium tin oxide. And does not depend on the difference in work function of the electrodes. So the electrodes can consist of the same material, say gold, while the device still operates at a low voltage. On the right is an example of the structure Again, just one example of a light-emitting electrochemical cell. So we're looking at encapsulation layers here, an aluminum cathode, an active layer, a PEDOT-PSS layer, ITO, and then ultimately this is on glass. So our active layer here is a mixture of super yellow, PEO, and KTF. Super yellow is a light-emitting compound, and KTF plus PEO, which is potassium trifluoromethane sulfonate and polyethylene oxide, is an electrolyte which provides the electrochemical doping needed for the LEC behavior. I forgot to mention the PEDOT-PSS layer is a smoothing layer. And finally, we have the encapsulation layer on top, which is resin and glass. So just like we did in the other examples, we'll characterize this step by step. So the first step here would be to characterize the graded ITO layer. So again, we have index grading. You can see on the right the optical constants of the top and the bottom of the ITO. This ITO is around 1565 angstroms thickness from ellipsometry. And on the left, you have the raw data and the fit results. ITO here is based off of a multiple tau Lorentz plus a Drude dispersion. So you can do this with many different dispersions. You can either use multiple tau Lorentz plus Drude or multiple new amorphous plus a Drude, whichever works better. The second step is to characterize the PEDOT-PSS layer on the ITO and glass substrate. So the structure here, bottom right, is 441 angstroms from ellipsometry of PEDOT-PSS on 1540 angstroms of graded ITO on glass. On the left is the raw data, again from ellipsometry, and the fit results based off of the model that you see there. And on the right are the optical constants of the PEDOT-PSS layer. So PEDOT-PSS here is modeled off of a multiple tau Lorentz plus a Drude dispersion. Again, you can try, instead of multiple tau Lorentz, you can try multiple new amorphous plus a Drude. The third step here is to characterize super yellow, since we don't know much about super yellow optically. And the super yellow here is on top of the graded ITO, and which is on top of the glass. So on the left, you see the raw data from ellipsometry and the fit results. And on the right, the optical constants of super yellow. So this is quite a complex material. And you can see it from the actual structure of the super yellow material. Here, we needed to add surface roughness of about 73 angstroms because we are sensitive to some surface roughness on the super yellow layer. And here, the super yellow is modeled based off of a multiple tau Lorentz dispersion, or again, you can try multiple new amorphous. The fourth step is to look at the PEO plus KTF on ITO and glass. So we have 236 angstroms of PEO plus KTF on, again, 1580 angstroms of graded ITO on glass. And you see on the left the raw data and the fit results. And on the right, the optical constants of the mixture material, PEO plus KTF. So PEO plus KTF, you can see, has quite interesting optical constants. They're very simple because K is 0 over the range that we're looking at, and N is decreasing with wavelength or increasing with increasing photon energy. So this tells me that PEO plus KTF is a transparent material. Has no absorption over the range that we're working with. So we can use simple single Lorentz oscillator to model this material. The fifth step here is to characterize a blend layer, just like we did for the P3HT and the PCBM. This is a super yellow plus PEO plus KTF blend. Again, on the left are the raw data and the fit results. Below that is the model. So this is super yellow plus PEO plus KTF on PDOT PSS, ungraded ITO on glass. And on the right, you'll see the optical constants of the super yellow blend. So notice when we blend super yellow and PEO KTF, it's no longer a transparent material. Finally, we want to characterize the entire LEC with the encapsulation. So we run into some problems here where we can't exactly measure from the super yellow side because the aluminum is completely absorbing. And the encapsulation layers are, of course, on top of the aluminum, and they don't help with the measurement either. So what we can do here is actually flip the sample upside down and measure through the glass. So you see the model is flipped. The top layer now is a surface roughness of glass, which we are sensitive to, and we do need to take that into account. Then the glass itself, then the ITO, the PDOT PSS, and finally the blend of super yellow plus PEO plus KTF. On the left, you'll see the raw data and the fit results for this entire structure. So with all of that, in conclusion, spectroscopic ellipsometry is a powerful, non-invasive, non-destructive, and non-contact optical technique. It's useful for characterizing thickness, optical constants, bandgap, composition, and crystallinity, and it's extremely important for materials used in organic devices. And the ones we discussed were ALQ3, NPB, CUPC for OLEDs, P3HT and PCBM for organic solar cells, and super yellow, KTF, and PEO for light emitting electrochemical cells. And of course, there are many other organic materials which can be characterized using SE. We just can't present all of them here. And as we learned, it's very helpful to have single layered samples for SE analysis in order to help reduce correlations, and it's also helpful to take the modeling step by step. So if you do need to use multiple dispersion functions, start with one on a smaller spectral range and then add on as needed. So before we end, I just want to point out that our next SE webinar is Thursday, October 20th at 10 a.m. Eastern Time. And it will be on optical characterization of CIGS by spectroscopic ellipsometry. And it will be given by our application scientist in France, Céline Iper, and Dr. Arnaud Etcheberry, who's the director of the Levasseur Institute in Versailles, France. So if you're interested in that webinar, you can visit www.horiba.com/ellipsometry, and you can register using the button on the right-hand side of the website. And I want to thank you very much for joining us, and thank you for your attention.
Thanks, Michelle. If anyone wants to submit a question, just know you can type it in the box below the presentation screen. We don't have a lot of time, so let me get to a few that I have. First question is, can we monitor the thickness and optical constants of these organic materials in real time on a roll-to-roll production line?
Okay, so that's a good question. And sorry. Okay, so that's a good question. And yes, so spectroscopic ellipsometry is non-contact. And it's a fairly quick technique, so it can be easily integrated into a roll-to-roll production line. Of course, we need to take certain precautions. We need to make sure that the sample is as flat as it can be and that the amount of vibrations are minimized as well. We currently have a customer that I'm aware of in Greece who is using spectroscopic ellipsometry on a roll-to-roll line. And he's actually characterizing nanomaterials for organic electronic applications. And if you're interested in seeing, he actually gave a webinar a few years ago, and if you're interested in seeing his webinar, you can also view that at horiba.com/ellipsometry. And you'll need to look at the Ellipsometry Academy and the webinars button, and you'll see that Nanomaterials for Organic Electronic Applications webinar on roll-to-roll applications.
Next question is, you mentioned the importance of selecting a spectral range for measurements. Can you expand on the ideal spectral range for the types of materials discussed here?
Yes, so the most important spectral range to have for these types of organic materials would be the near infrared. And the near infrared is very useful for determining accurate band gaps for materials. And of course, the NIR can also help if your samples are very thick. However, if your samples are ultra thin or if they're on plastic substrates, it's probably also helpful to include the UV region as well.
The next one is, sometimes our wafers are patterned. Can we still use SE, and if so, what's the limit on size that can be measured?
So yes, of course, spectroscopic ellipsometers have the capability to have microspots, which allow for the measurement of patterned or contaminated wafers. Also useful for curved areas or other small areas of interest on your sample. And just to point out that the smallest available microspot on an instrument that we have here at HORIBA is the Auto SE, and that size is 25 by 60 microns. So as long as your feature is larger than that spot size, you can measure the feature and you won't have any issues with that.
Do you have issues with backside reflections from glass, and if so, how are these handled for the data that are shown?
Okay, so glass and transparent substrates typically have a problem with back reflections, if you're familiar with doing ellipsometry. And the back reflections can overlap with the actual measurement spot. So of course, if you have a HORIBA ellipsometer, it's not such an issue to include the backside reflections into your measurement, as corrections can be made in the software. With a CCD-based ellipsometer and a substrate thicker than roughly 0.4 millimeters, you can automatically block out the backside reflection if you need to, because the field of view of the CCD chip is quite small. And then in that case, only the top reflection will be measured. However, if you have a scanning system, the thickness limit is about 1 millimeter. So if your substrate is thicker than about 1 millimeter, you can see the difference between the top reflection and the back reflection, and you can use small objects such as wires or pieces of paper to block the back reflection and only measure the top reflection. Of course, that's helpful because it leads to one less step in the modeling process, so you don't have to take anything into account in the actual model, so it makes for a simpler model.
If we have many routine multi-layered structures to measure, say OLEDs with the same structure, do we need to characterize single layers for each multi-layered structure?
Okay, so in general, no. If your materials are deposited by the same technique every time, and they stay relatively the same, once you determine the optical constants for the single layered samples, you can use them at least as a starting point in the model for the complete stack. And that will help you determine just the thickness. It'll reduce the correlations that you have for the complete stack. And it'll also help make your modeling just a little bit simpler. So you'll have the optical constants already there, and all you're focusing on then are the actual thicknesses of the materials that are in the sample.
Can you comment on the difference between a Tauk-Lorentz oscillator and a new amorphous oscillator? Which one should I use?
Sure. So generally speaking, both the Tauk-Lorentz oscillator and the new amorphous oscillator have 5 fit parameters, and both can be used for similar materials. But what they are in reality is just a different equation, different mathematical equation that you use for modeling. Our suggestion here would be to try both oscillators, try the Spectral Range, try the new amorphous, and see which one works better for the material. So you noticed for OLEDs and organic solar cells, maybe the new amorphous worked a little bit better than the Spectral Range, whereas for the light-emitting electrochemical cells, the Spectral Range worked a little bit better for that case. And you can check which one works better by, of course, looking at your overall results. So again, we're looking for goodness of fit, the correlation matrix, the confidence limits, and whether the optical constants are physical, whether we have a K that is positive, and the overall shape of the optical constant.
Hi, I notice you use glass substrate for OLED but use Si substrate for OPV for the fitting. Is there a specific reason?
Okay, so you can use whatever substrate that you want. You can use glass, you can use silicon, and all you're basically using it for is to determine the optical constants of the material on top. So in some cases, it's easier to determine the optical constants of a material that's on a silicon substrate because silicon is very well known and characterized, whereas if you have a material on glass, you have to actually analyze the glass first, bare glass, before analyzing your actual sample. So you can pick and choose whichever substrate you want to use. The only differences are, like I said, silicon is typically easier. Glass can present the backside reflections and things like that. But if your overall device is on glass, then you might as well keep everything on glass and analyze it that way.
What is chi-square values of your fitting for P3HT and PCBM?
Okay, so typically, just to give kind of a more general answer for chi-squared values, we want chi-squared to be around 1. Some of these materials will be a little bit more complex, and we'll get a little bit higher chi-squared, but we generally want to make some modifications to the model such that we get a good chi-squared of around 1. So I don't have the specific values for P3HT and PCBM, but I'm sure that they were pretty close, below about 5.
Yes. What? Have you run into any issues with the UV measurements where the UV degrades the organic material, or is it a very low dose?
Okay. So as far as UV measurements, the ellipsometers are typically equipped with a UV filter to help block out the UV light that's hitting the material. So that's not normally a problem with the measurements that we do here.
Okay, so that's all we have for now. Thanks, Michelle. If anyone wants to submit questions, you can send them to me at the email when you get the response email, and we can follow up. I also want to just let you know that if you have any other questions about ellipsometry, you can go to our website, HORIBA.com, ellipsometry, and there's an Ellipsometry Academy button where you can do a lot of research and check out webinars and FAQs and introductory information. I want to thank everyone for their questions and participation in today's event. This webcast will be available for on-demand viewing through October of next year. You'll receive an email from On24 letting you know when it's available. We invite you to forward the announcement to any colleagues who may have missed today's event, and certainly you can review it yourself at any time. We look forward to seeing you next time. Thanks again. Bye.